So this was the gmesh file, the mesh file which we built for our simple monopole 2D case. So we developed this in the previous talks. So now let's and also we just exported it and created this circle.m file, right? So this is the gmesh exported file in MATLAB format, and so now we just have to read this in order to create our element to node connectivity list and our boundary elements list, our nodes list, and so on. So we have already done this for the 1D case, and for the 2D case the procedure will be very similar. So for the 1D case I think I have provided a pseudocode, but in this case I will be providing the full code in MATLAB, and I will also provide a code in Python and Julia for the 2D case. So in case of Python we'll just be able to read the .msh file. For Julia I did not find such a good working mesh reader, and so I have just developed this mesh reader by myself, and really you can use AI to do this, and there is no finite element related logic there. So so let's look at the structure. So the structure is very simple and similar to the 1D case. So you just start off with the total number of nodes, then you have the x and y coordinates. So the first row is the first column is the x coordinate, the second column is the y coordinate, and so the first row stands for the first node, and so on. So the order of the nodes is obviously scrambled, but gmesh will obviously maintain the same order for all of these arrays. So this is the xy coordinate array, and then you have the lines array. So in this case lines are the line elements, and the only line elements here are the boundary elements. So you can see that they have a flag of 3. So 1 and 3, so we are using linear elements. So there are only 2 nodes per every line. So the first element is 1 and 3, and then you have the 3 which is the flag for the inner boundary. So if you just change this, you can see that you have 1 and 3 here. So this is your line element, and 3 is just the flag, very similar to the points that we read. So you just had points here in case of 1D mesh. Now you just have lines, and you have the 3 number flag. So all of these elements are your interior boundary elements, and on the exterior boundary you have these elements which are flagged with 4 at the end, right? And so after this you have triangles. So triangles are your triangular elements, and all of them are flagged with 5 because the physical group tag is basically 5. So the first 3 columns are your node numbers. So we can just read it in a very similar way to our 1D case, just that. So this was our 1D case, and we just read the lines and the points. So the points were the boundary nodes, right? And the lines were your elements, right? So in case of 2D, the mesh will just do something similar, just that triangles will be your elements. So element info will be built with triangles, and your boundary info will be built with lines. Okay. So this is a simple mesh reading file. You can even just put this kind of a file into OpenAI or DeepSeek and ask it to make this mesh, or you could just write it yourself. Nothing related to finite elements here. So let's just stop here. So now we know how to read our mesh. Let's just call the mesh once, so that we just get an idea of how the struct will look. And as I mentioned again, you have the struct in case of MATLAB, and in case of Python and Julia you you have dictionaries. So let's just call circle.m, and here I have added excluded flags. So this will be applicable for the next 2D problem. So let's just leave it as it is right now. So we are just going to read all of the flags. We are not going to exclude anything. So now we have got the struct. So you can see it in the workspace, and here you have elements. So this is our element to node connectivity list. This is our boundary info list. So flag 3 has all of these elements, flag 4 has these elements, and so on. And in node info you can get the X and Y data. Right. All right. So these are our node IDs, and we have just put them in ascending order. So that's about it. So this is how we read our mesh, and now we can use this mesh reader and just plug it into our 1D solver and convert it into a 2D solver. So this is our live 1D solver which we designed by plugging in the gmsh mesh. And now let's just modify it for the 2D case. So first let me just explain those parts that we are going to modify. So before we do that, let's also probably have a look at the shape functions again. So let me just plot the shape functions once again. So we are just going to plot, we are just going to use P1 functions here, and you can recall this is a 6-point Gauss rule here that I have used. So these are available on the internet, and you can choose the rule which you want. And so I have used a 6-point Dunavant rule, and in Dunavant's original paper I think they have defined from the centroid, but in my case I have just defined these points from as per psi and eta, because that is the nomenclature that I am using. So you just have to, so when you are exporting or importing basically the Gauss points from literature, you just have to be sure that you are doing it correctly. And so the procedure will be really similar. So we just have X and Y coordinates for our Gauss points, and we can just instead of putting just one value of Gauss points, we have to put both values. So we just run over these 6 Gauss points, multiply by the Gauss weights, and the Gauss weights should be scaled with 0.5 if they have not already been done so, to ensure that the area, so the area of this master triangle is 0.5, so we have to ensure that. One thing that we discussed is how to look at the boundaries. So we want to prescribe the boundary condition, Robin boundary condition. So in this 1D case, we had simply done this by this one line, because we had a point integral. So now we have a line integral, and so we will need to actually prescribe elements there. So one way to do that is to actually use the element, and so for example, if I am using this linear triangle, and let's say I want to integrate over this boundary, so I already know that this refers to, so this boundary is basically eta is equal to 0. So I can just put eta is equal to 0, and I could integrate over this element using the same shape functions, and I would just be integrating over this line. Okay. And I could also put psi equal to 0, and I would get this line, or the third case after eliminating these two is just this line. So this is one way of doing the integration, but more easier way of doing this is just to understand that these triangles, these triangular elements are exactly prescribing the linear shapes, the 1D linear shapes at the boundary. So you can see here. So you are just getting the 1D Lagrange polynomials at the boundaries. So this is like psi, and this is 1 minus psi. So I think we already showed this for this case, right? For the P2 case, it's more evident here. So you can see this is your quadratic shape function for 1D. So already on your boundaries, you have these functions. So you can just define them and integrate over 1D shapes directly. So if we are using linear triangles, we can just use linear shapes at the boundary, and we can just integrate it directly. And then we can add it to the integral at the boundary nodes, and that will be our boundary integral. So we have to add this to the stiffness matrix, right? Because we have unknowns in your Robin boundary, because your Robin boundary is containing the sink or source terms. So the unknowns have to be brought to the stiffness matrix, but these are boundary integrals, and the stiffness matrix has an element level integral. So we just have to add these boundary integrals at those boundary nodes. And so this will take care of the Robin boundary condition. So that's how we are going to implement, and rest of the changes are really small. So instead of just having one of these dn into dn transpose terms, you will have two, one for x coordinate and one for y coordinate. We won't have this radius term. Your L will just become your determinant of J. So for that we will have to just change this isoparametric mapping, and we will have to calculate the J matrix here, and the shape function library will also change. Besides that, then of course we'll have to change the plot as well. We'll just use a scatter plot, and this solution will not be applicable anymore. So we have a logarithmic solution. All right. So that's about it, and we'll just change the Gauss rules as well. So let's just start doing this step by step, and let's just copy this to the next. Let's just generate another. Okay, so I guess right, I have this. All right, so I have this here. So let me just start off coding this 2D solver. So let me just make a copy of this and start off.